Hi, and welcome to mini lecture 2 for week 5 of Thermodynamics for Educators.
In this lecture, I'm just going to give you a quick look at the 3 simulations that you'll be looking at this week, just to show you how they work. The first 2 are aimed at demonstrating how systems approach equilibrium and trying to connect this with the second law of thermodynamics as it is stated in terms of multiplicity. So firstly, there is a coin flip simulation, different from the one that you saw last week, which I'll now open up. So when you open it up, you'll see the following windows appear. The introduction gives you the basic instructions on how to use this, and it's very simple. What happens is the system starts off with a certain number of coins, and those coins are all heads up. And you can change the number of coins that are flipped. The picture itself doesn't change, it always shows 50 coins, but the simulation will run results for however many you put in here up to a certain limit. So you can explore how things change when you increase the number of coins. So we'll start off with 50 here. So what the simulation is going to do is that it's going to randomly select a coin and flip it. And that coin will either come up heads or tails. And then it's going to randomly select another coin and flip that, and randomly select another coin and flip that, and so on, and it'll just keep going. And what will be plotted here is the number of coins that are heads up and the number of coins that are heads down or tails up. So when you hit play, it will start flipping coins, and it'll do it very quickly, and you'll see how the number of heads and tails evolves as time goes on, like this, as a function of the number of flips. Okay. And this is a visual representation of what the distribution looks like. This demonstrates the concepts of approaching equilibrium from a starting state, and it also illustrates the concept of thermodynamic fluctuations. Part of the homework will be to explain how it demonstrates these concepts. So you can pause this whenever you like, and you can reset it, and you can say bump the number of coins up. Let's try 500 and see what happens then. Okay, let's quit that and go to the second demonstration of approach to equilibrium, which is the interacting Einstein solids demo. Okay, so what this does is you have 2 Einstein solids, A and B, and you can set the number of oscillators of each to be whatever you want. So they're currently set to have 81 oscillators each. So if you're thinking physically, remember each atom can be described by 3 oscillators. So this would correspond to 27 atoms in each solid. Okay, then QA and QB are the number of energy units that we are going to give the system as a whole. So QA plus QB is 9, means that we're going to distribute 9 energy units among the system, among the 2 solids. And at t equals 0, at time equals 0, we're starting off with 0 energy units in solid A, which means that all 9 units must be in solid B. Okay. Now, there's a plot here of the entropy, which we are not going to look at yet. We haven't got to defining the entropy of the system yet. But what we can look at is the energy histogram. So when you click on that, this graph will appear here. So what you'll see here, the square dots here show what the equilibrium, what the multiplicity function looks like for each of these solids. Okay, so you can calculate it yourself. Last week we saw how to calculate this function. And you see that it is peaked in the middle when you've got 4 to 5 units of energy in each solid. That's when there are the most ways of, the most microstates, most ways of arranging those 5 units or 4 units amongst the available oscillators. Okay, so once you've set it up, you've set up your number of oscillators, your total energy, and the energy that's going into solid A at the start, then what the system is going to do is it just randomly takes one of these 9 units of energy and places them in some random oscillator in either solid A or solid B, selected completely at random. And then the next step, it does exactly the same thing. It picks one of these 9 at random and places them randomly in some oscillator somewhere in A or B, and so on. So it keeps randomly just picking an energy unit and redistributing it somewhere else at random. And so let's see how this evolves. So the step forward button allows you to go one step at a time. So if you click it once, you'll see that it's taken 1 unit of energy and it's placed it Okay, so what the simulation does is it takes a random number of these units of energy and places them in some random oscillator somewhere in this system. Okay, somewhere in A or B. So and at each time step, it takes a random number of the energy units and places them somewhere randomly in some of the oscillators of A and some in B. So if you click on Evolve, it will keep doing this. It'll keep selecting units at random and placing them somewhere in solid A or solid B. And so you can watch how the distributions change over time, and as time goes on, the distribution of energy amongst the oscillators in solid A and solid B approaches the equilibrium value. Down here, you get the average value of the number of energy units in solid A and solid B, and you'll see that they approach 4.5. So resetting again, they start off at 0 and they approach 4.5. Again, this shows the approach to equilibrium from some starting point. Now, if you want to change any of these parameters, just to give you one tip, if you, say, wanted to change the total number of energy units to 40, then you enter 40, you have to hit enter for that to take effect. And let's say you want to change the number of units of energy that A starts off with to, say, 5, you have to hit enter again. Then you can evolve in time. You need to switch on your energy histograms and you can watch them evolve in time with the new sets of parameters. Okay, the final thing I want to show you is a simpler version of this that just gives you the multiplicities, microstates, and probabilities for 2 Einstein solids that are isolated from the outside environment. And this is a way to check what you've been working on in the 2 tutorials that you did last week. So for example, if you have 9 oscillators in each solid and 3 energy units, you have to hit return every single time you make a change like that. When you hit return, it will calculate a table of the multiplicities corresponding to the 4 macrostates. Okay. Again, ignore for now this plot here. These plots are something that we will cover in the future.